the thing that we're going to be proving is that every regular language has a planar, non-deterministic finite automaton. And actually, the non-deterministic part is really important here, because if you replace this with deterministic machines, then this is not true. And I invite you to try to come up with an example of that. So we actually do need the non-determinism here in order to show that this is true. And the really nice thing about NFAs is that they're very similar to another object for regular languages called regular expressions. And the nice thing about those is that they are defined inductively. So we can apply a proof by induction to get a result like this to show that no matter what regex you have, there's a corresponding NFA that's planar. So let's look at how you would prove such a thing. We're going to be proving this by structural induction. So by induction in this case means that no matter what regular language you consider, the regex that corresponds to that language. So let's let L be any regular language and let R be any regex for that language L. Then that means that this regex involves one of 6 possible cases. The 3 base cases are the empty set, the empty string, or a single character, and the 3 recursive cases are the union of 2 other regular expressions, the concat of 2 regexes, or the star of a regex. The first base case is when R is the empty set. If we make the NFA corresponding to that, then that is a very simple NFA. It's just a single state that's not accepting no transitions, nothing. And there's no transitions that cross, and so therefore, this NFA is planar. And it's going to be very similar for the other 2 base cases. Namely, if R is the empty string, then we can have a very similar NFA, which is just an accept state this time. The third base case is a little bit harder, not super hard, where it's just a single character, let's call it A, where A is a member of the alphabet corresponding to L. Then what this NFA would look like if you just do the standard conversion would be a single transition. Well, there aren't 2 transitions to cause a problem, and so there's no issue here. So then now we need to go on to the inductive cases. So in every inductive proof, we need an inductive hypothesis, which all you do is you take the thing that you're trying to prove, and instead of say every or for all, you say for some. Actually, there's a little bit more you have to do because we're going to be looking at 2 regexes and then doing unions and concats and stuff. And so we need to make this inductive hypothesis be about 2 regexes instead of 1, but it's the same idea. So for some regexes, R1 and R2, there exist planar NFAs, N1 and N2 for them. And of course, N1 corresponds to R1, N2 corresponds to R2. So the first inductive case is when this regex that we're building is the union of the 2 smaller guys. Okay, so what will that look like? Well, if we just do the standard conversion, we have a new start state that epsilon transitions into the start states for the original 2 NFAs. Well, let's just draw what they look like. Well, if the N1 machine is up here and the N2 machine is down here, as long as we make it so that the N1 machine is suitably higher than the N2 machine, which we can always do, we can always make the transitions as long as we want, then we just move this start state as far left as we need to because these drawings are finite in size. And so therefore, this NFA is planar because we can just move the NFAs far enough apart. And if we did the second inductive case, which corresponds to concat, so R is R1 concat R2, then we can do a very similar idea where we take the N1 machine and the N2 machine, but we put the N1 machine to the left of the N2 machine. So the start state is the start state of N1, and there are epsilon transitions from N1's final states, however many there are, to the start state of N2. But as long as we move them far apart, and we have all of the final states of n1 on the right side, which we can do, as I'm going to briefly explain in a sec, then we can do this without any of these epsilon transitions running into each other. So how do you make sure that all the final states are on the right side? In all the base cases here, we have the final states on the right side. There aren't any here, but so all of them are on the right side. All of them are on the right side here. All of them are on the right side here. In fact, there's only one here. And you can always convert any NFA into an equivalent one, which has exactly one final state. And if we do this here and assume that N1 and N2 have their final states on the right side, then these have everything on the right side. And right here, all the final states of the conglomerate machine are on the right side. So as long as we make sure that star has every final state on its right side, then we're good to go. So to make some room, I'm going to eliminate these base cases, but we've already proven those, and those are super easy. So the third inductive case is R is equal to, let's say, R1 star. Then the standard conversion is to take the N1 machine, which corresponds to R1, and you have that be its start state. But what you do is you make a brand new final state at the beginning, epsilons your way into the start state of N1, and every final state of N1, the original box, epsilons their way back to this brand new start state. But not every final state is on the right side, because this state is over here. So the way to fix that is to have this state be not final, but to make a brand new final state over here that has an epsilon transition here, and from these guys, and also make them not final. So no matter what, because this is a non-deterministic machine, no matter whether you're here or one of these guys, there's always a choice to go over to this final state, and so it doesn't change the language of the machine. And all of its final states are on the right side, and combined with all the base cases, has exactly one final state on its right side. And so therefore, there's no issue with any of the recursive cases, because, so if you view N1 now in the context of the entire proof, all of the epsilon transitions coming back from N1's final states to this brand new start state, it looks like I've drawn more than one, but in fact, combined with all of the other recursive cases and base cases, there's exactly one. And so we can just have it go on top above N1, and because it's the rightmost state of N1 by assumption, and they come back if you have them go all the way over N1, and the transition from here just goes under all of this N1 business to this brand new final state. And it looks like there are multiple epsilon transitions here, but of course there's only one. And so therefore we have proven that every regular language has a planar non-deterministic machine.